Good morning, students. In previous class we have learnt kinetic molecular theory and deduction of gas law from kinetic molecular theory. So kinetic molecular theory can explain the behavior of gases by theoretically. Okay. Now we will discuss about real gases behavior. So next one is real gases behavior and how can deviate from the ideal gas behavior. So today class we will discuss. So here ideal gas, what happened here? Ideal gas is not, it is a hypothetical gas. So generally in the universe all are real gases, okay? So not a ideal gases, but they can act as a special conditions. At special conditions all real gases act as a ideal, okay? So now we will discuss about real gases behavior and deviation. Real gases deviation from ideal gas behavior. Now we will discuss. Okay. So real gases, all real gases can act as a ideally at certain conditions. Which conditions? At low pressure, as well as the high temperature. So all real gases can act as a ideal gases. At what conditions real gases can act as a ideal gases? Okay. So at low pressure and high temperature. So what will be happen at low pressure? If you take a container, in this gas molecules are there. So in this gas molecules are there. But at low pressure what happened? These gas molecules are each far away from each other. Okay. That means there is no attractions or repulsions between the gas molecules. At which situations? At low pressure. At low pressure gas molecules are far away from each other. That's why there is no attractions or repulsions are there. That's why real gases can act as a ideal gases. At which situations? Low pressure as well as the high temperature. What happened at high temperature? High temperature is nothing but if the temperature is increases, molecules kinetic energy is also increases. That means molecules are far away from each other. So that's why here is also at low pressure and high temperature molecules are far away from each other. That's why there is no attractions or repulsions there. That's why real gases can act as a ideal gas behavior. At which situations? Low pressure and high temperature. Next one is, if at high pressure, if you take a high pressure and low temperature, what happened here? At high pressure means molecules are come close to each other. Next, low temperature is also, if the low temperature means temperature decreasing means speed of the molecules will be decreases. That's why gas molecules come close to each other. Whenever molecules are come close to each other, what happened here? There is a significant of repulsions as well as attractions are there. That's why real gases so deviate here, real gases deviate from ideal gas behavior. At which conditions? At high pressure and low temperature. Now to explain the deviation of real gases from ideal gas behavior, scientists had studied the effect of change of pressure on PV. So this is a graph. Okay. So several gases here, experiment is done on several gases. So what is that? Here we taken a PV, the product of PV is taken on y-axis and the pressure is taken on the x-axis. Several gases here, we find out the gases, which one is behavior of the carbon monoxide gas and methane, hydrogen and the helium. Okay. So scientists had studied the effect of change of pressure on PV of several gases at constant temperature, that is 0 degree centigrade. 0 degree centigrade, or it is nothing but 273.15 Kelvin. So this is the temperature. This is the temperature. At this temperature, scientists studied the behavior of carbon monoxide and methane, hydrogen and helium is taken. Okay. So here this straight line is parallel to the pressure. So this straight line is called ideal gas. This is an ideal gas behavior. So ideal gas can give the straight line at all pressures. At all pressures, ideal gas give the straight line. Which straight line here? The product pressure and the volume values here are parallel to the pressure. So this is belongs to the ideal gas behavior. Here two types of deviations are there. So one is here two types of deviations are there. One is one deviation is belongs to the hydrogen and the helium gases, and the another deviation is carbon monoxide and methane gases. Okay. If here, so these real gases, which are the hydrogen, helium, methane and carbon monoxide, so these also can act as whenever can act as a ideal gas. So these lines is nothing but as a straight lines, but here what happened, some deviations are there. So from this we can conclude that real gases not coincide with the ideal gases at all pressures. Okay. At which pressures? At very extremely low pressure. This is a extremely low pressure. So in this extremely low pressure, all real gases can act as a ideal gases. Why? Because at extremely low pressure what happened? Molecules are far away from each other. Far away from each other. So far away from each other is nothing but there is no attractions or repulsions are there. That's why all real gases can act as a ideal gas behavior only extremely low pressure. Only extremely low pressure. All real gases show ideal gas behavior when pressure approaches to 0. The pressure approaches to 0. All real gases show ideal gas behavior. So now we will see the behavior of hydrogen and helium gases. Okay. So they show the positive deviation as the pressure increases. As the pressure increases, the PV value is also constantly increases like this. Okay. So from this we can conclude that hydrogen and helium gas can exhibit the positive deviation. Positive deviation. Now second types of carbon. Second one is for the carbon monoxide and methane gas. As the pressure increases, what happened? The PV value gradually decreases at firstly. Gradually decreases. And further again pressure will be increases. That what happened? It's a gradually decreases and the minimum is reaches to the minimum. Here minimum. And further again pressure increases. These are the like this PV value is also further again increases. So these are which are the carbon monoxide and methane can show the negative deviation. Negative deviation. Okay. So from this is also we conclude that some gases can exhibit the positive deviation, some gases can exhibit the negative deviation. But what happened at approaches to 0 pressure, that means at approaches to very low pressure, all real gases can act as a ideal gases. So finally from this graph we can conclude that real gases at low, very extremely low pressure, they can act as a ideal gas. But whenever pressure will be increases, some gases can exhibit the positive deviation, some gases can exhibit the negative deviation. So real gases are not act as a ideal gases at all pressure conditions. That means all pressure cannot act as a ideal gases. Next, another graph also can exhibit the real gases can deviate from the ideal gases behavior. So here is also what happened. The graph, we can draw the graph between the relationship between the pressure and the volume at constant temperature. Okay, so already we know that Boyle's law, it is a, which curves are there? It is a hyperbola curves are there. But in this hyperbola curves, what happened at extremely low pressure? So this is a extremely low pressure. So extremely low pressure, the volume of real gases is coincide with the volume of ideal gases. But whenever the pressure increases, what happened? Real gases volume is more. Real gases volume is more compared to the ideal gases volume. So from this is also we can say that not all conditions, not all pressure conditions, real gases can act as a ideal gases. They are the deviated at which situations? At high pressure. Okay, so already we know that at high pressure what happened? At high pressure molecules are come close to each other. That's why there is a repulsions as well as attractions between them. That's why they are the deviated from the ideal gas behavior. So these two graphs can explain conclude that from these two graphs can explain real gases deviate from the ideal gases, and real gases can act as a ideal gases only certain conditions only. Not always real gases can act as a ideal gases. Now causes for the deviation. So what is cause? What is the cause? Okay, so van der Waals assumed that the deviation of real gases from ideal gas behavior is due to two wrong assumptions in kinetic molecular theory. Okay, so he said that two wrong assumptions are present in the kinetic molecular theory, which are, first one is, that is A. So there is no attraction force between the molecules. There is no attraction force between the molecules. There is. So first one is there is no attractions or repulsions between the gaseous molecules. And the second one is volume of the molecules, gas molecules, is negligible when comparing to the container volume. So these two wrong assumptions, that's why real gases can deviate from the ideal gases behavior. Okay, if so, how are it wrong? So we can study. Okay, if there is no attractions or repulsions between the molecules, what happened? If A is correct, for example A is correct, gas will never liquefy. But in practically or in our real life, nitrogen can be converted into liquefy. Hydrogen is also can converted into liquefy gases. Okay, if there is no attractions or repulsions between them, what happened? These gases will never liquefy, but practically these are the liquefied. Okay, so that's why this is wrong assumptions. And next one is volume is negligible. If volume is negligible, this is a, for example, it is a right. What happened in our graph? So both volumes are coincide. Both volumes should coincide. But here what happened? At some conditions, they are the deviated. So that's why here, so this assumption is also wrong assumptions. So these two are wrong assumptions. So that's why real gases deviate from the ideal gas behavior. So this can explained by the van der Waals. Now van der Waals deduced a equation of state for the real gases by correction of two factors which are pressure correction, and the second one is volume correction. So this is the first one, this is second one. Now we will see the correction of pressure. So what happened here? At high pressure, gas molecules are close to each other. If you take a container, what happened? At high pressure, gas molecules are come close to each other. So what happened at that situations? Attraction forces are present between them. Okay, for example, it is a gas container. Next, due to these attraction forces, gas molecules could not exert pressure strongly on the wall of the container. Okay, for example, this is a wall of the container. So here in this two types of molecules are there, that is a type molecules, and next one is a B type molecule. So in A type molecule, is attracted equally by all gas molecules. Okay, in equal side, all are. So that's why the net force of the attraction on the A molecule is 0, because A molecule is attracted by all molecules and equal directions. That's why net attraction force will be 0 for A molecule. But B molecule, what happened here? Some molecules are dragged to B molecule from back side. So what happened here? The force of here, the pressure is not strongly on the walls of the container, because some molecules are dragged to back. B molecules. Okay, so what happened here? Pressure is very less compared to the ideal. The pressure exerted by the B molecule, the pressure is very less compared to the ideal gases. Okay, in ideal gases what happened? Molecules are, there is no attraction force and repulsion force between them. That's why here the pressure is strongly. At high pressure what happened? Molecules are come close to each other. That's why B molecule is drawn back to the some other molecules. That's why exerted pressure is very less. So here exerted pressure is very high. So this is the ideal gas behavior. So this is a real gas behavior. Okay, so that's why the pressure exerted by the real gas, is very less compared to the pressure exerted by the ideal gas. In ideal gas, molecules are far away. That's why here strongly exert the pressure. But here whenever the molecules are come close to each other, what happened? The B molecule exert the pressure is very less compared to the ideal gases. Okay, now here what happened? To balance this, what happened? For example, this is the ideal gas pressure. To balance this, the real pressure plus add the some pressure correction factor. Here we add the some pressure correction factor. Now the balance. Okay, so we know that two types of molecules are there. So that's why here concentration of A type molecules, the concentration of A types molecules is N by V. So visualize the concentration of B type molecules is also N by V. Now from this we can say that the pressure is directly proportional to concentration of A molecules and the concentration of B molecules. Okay, so now here from this we can conclude that pressure is directly proportional to N by V into N by V. So now here P is directly proportional to N square by V. If you removing the proportionality, what happened here? P equal to A N square by V square, here V square. So this here, where A is van der Waals constant. Van der Waals constant. So this is a pressure correction factor. So from this we can say that is a P ideal equals P real plus A N square by V square. So this is called pressure correction. This is called pressure correction. Next one is volume correction. At high pressure, the volume occupied by the gas molecule is significant. Okay, so in ideal gases, for example, this is a ideal gases volume. That means in ideal gases, what happened? The molecules in ideal gas, molecules are point masses. Point masses means volume is negligible whenever in ideal gas situations. But in real gases, what happened? At high pressure, what happened? The volume at high pressure, the volume will be decreases. So in these situations, what happened? The volume of the molecule is not negligible. Here significant is there. Okay, so in what happened at high pressure, the volume occupied at high pressure, the volume occupied by the gas molecules is significant. So that's why van der Waals suggested that a correction of factor B for 1 mole of gas, that is a P ideal equals V real minus B for 1 mole of gas. If you take an N mole of gas, is a V ideal equals V real minus NB. So this is the correction of the value. So this is equation 2. This is equation 1. So from this correction of the pressure and volume, the ideal gas equation, that is a PV is equal to nRT, it will be changed after the correction, that is P plus A N square by V square. This is the P, correction of the P. Next, correction of the volume, that is a V minus NB equal to nRT. So this is called equation of state for the real gases. So this is called equation of state of real gases, and it is also called van der Waals equation. Van der Waals equation. So this is a very, very important equation for the multiple choice as well as the derive the van der Waals equation. Very, very, very important. So van der Waals equation, once again repeated, is a P. It is a correction of the pressure, that is A N square by V square. Next V, this is the correction, pressure correction factor. Okay, sorry, volume correction factor, V minus NB. Okay, so A and B are van der Waals constants. A and B are van der Waals constants. Okay, and A, B values are depends on the nature of the gas. So A and B values are depends upon the depends upon the nature of gas. and a particularly A is the magnitude of intermolecular attraction forces. Is A is independent of temperature and pressure. So this is the information about van der Waal equation. So van der Waal equation is nothing but equation of state for the real gases. So it is deduced by the van der Waal. That's why this equation is called van der Waal equation. Okay. So once again repeated here, real gases behavior, that is a deviation from ideal gas behavior at low temperature and high pressure. Real gases can act as ideal gases, but at high pressure and low temperature real gases deviated from the ideal gases behavior. So we know that already. Explain the why, because at that situations they are deviated, sometimes it is coincide with the ideal gases behavior. Okay, next, causes for the deviation. Van der Waal suggested or assumed that there is a two faulty assumptions in kinetic molecular theory, which are there is no attractions or repulsions between the molecules. So this is a wrong assumptions in kinetic molecular theory. Next one is volume is negligible. This is also wrong assumptions. So from this van der Waal suggested that after the correction of the pressure as well as the volume, he deduced the equation of state for the real gases. So this is called van der Waal equations. Now another topic, last topic in the gas state, that is a compressibility factor. So now this is a compressibility factor. So compressibility factor can represented by the Z. Okay, the deviation of real gases from the ideal gas behavior can be measured in compressibility factor. So how much the deviation can be measured by the compressibility factor. Okay, and which is the ratio of the product of PV and nRT. So this is the ratio of, mathematically can say that the compressibility factor is nothing but PV is divided by nRT. So this ratio, and we will the graph for the ratio, that is a compressibility factor Z, as well as the pressure. So pressure is measured in the bar. So here is also some graphs are there at constant temperature. Okay, so at extremely low pressure, so this is called extremely low pressure. At extremely low pressure, Z is very close to 0. That means Z is very close to 0 means it is a unity. So which indicates that all gases behaves as a ideally at extremely low pressure. So first one is, from this graph we can conclude that at extremely low pressure, what happened, the value of Z is equal to 1, approximately Z is equal to 1. At very high pressure, so this is a very high pressure, from this is very high pressure. Okay, so at very high pressure what happened, Z is greater than 1. Second one is, at very high pressure, Z is greater than 1, like this, hydrogen. So which R can exhibit the positive deviation? So these gases can exhibit the positive deviation, which indicate these gases are less compressible. So hydrogen, helium, they are deviated, so they can exhibit the positive deviation, and that's why these are difficulty to compressible. Compressible is very difficult because here dominates the molecular repulsions. So these are here dominant the molecular repulsions. So that's why these gases, compression of these gases is very difficult. So the question is rising, so which of the gases can difficult or more difficult whenever the compressible? So which of the gases can exhibit the positive deviation? So those gases are compressible is very difficult because here repulsions, molecular repulsions are predominant. Okay, and next one is at moderate. So this is called moderate pressure. At moderate pressure, what happened? Third one is to moderate at moderately low pressure. What happened? Z is less than 1. That means the gases can exhibit the negative deviation. Okay, so these gases are more compressible. These gases are more compressible because at moderate low pressure, what happened? The molecules are here come close to each other. That's why here compressible is very easy. So here is also dominance of long range of attraction forces at moderately low pressure. That's why which favor the compression. So which gases here? Carbon dioxide and methane and oxygen. So these are can exhibit the negative deviation. That's why here, sorry, this is the nitrogen. Okay, so that's why here these gases, negative deviation gases, are compressible easily because at moderate low pressure some attraction forces are there. Okay, so this is the information from this graph. And next, the very important, the temperature at which real gases obey ideal gases law over an appreciable range of pressure is called Boyle's temperature. Boyle temperature or Boyle point. Once again repeated, the temperature at which a real gas obey ideal gas laws over an appreciable range of pressure is called Boyle temperature or Boyle point. So Boyle point of a gas depends on its nature of the gas. Boyle point of a gas depends upon the nature of the gas. Next, above the Boyle point for the real gases is Z is greater than 1. Above the Boyle point, that is real gases show positive deviation. Real gases show positive deviation above the Boyle point. So this is above the Boyle point. Next one is below the Boyle point. Below the Boyle point, real gases first show the decreasing the Z values. Next, below Boyle point. So first of all, the Z value will be gradually decreases and reaches a minimum, and after that pressure will be increases, that Z value will be increases. Okay, so below the Boyle point, real gases first to show the decreasing the Z value and reaches a minimum, and next one is that increasing whenever the pressure will be increases. Okay, so that's why here real gases show that is Z is less than 1. That's why these gases show below the Boyle points, gases show the negative deviation. So finally, from this information we can conclude that at low pressure and high temperature, real gases show ideal behavior. And finally, we know that Z for the real gases, that is a Z equal to PV, that is real, by nRT. For ideal gas equation, that is a PV ideal equal to nRT. So from this we can conclude that P ideal equal to nRT by V. So from this we can conclude that I will write here Z equal to V real by V ideal. So compressibility factor is also the ratio of molar volume of real gases as well as the molar volume of the ideal gases. So this ratio is also, we can conclude that, compressibility factor, and compressibility factor can determine or measure the deviation of real gases from the ideal gases behavior. So this is the conclusion.